Good morning. Welcome to Managing Workplace Heat Stress with Air Movement. I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session worth your while. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. Lastly, this session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. With that out of the way, let's meet our presenter. David Rose joined Big Ass Fans in 2015. Currently, he serves as Global Product Manager for all high-volume, low-speed products and an array of design assistance software. Previously, he led a multidisciplinary team of engineers dedicated to technical business development initiatives and application design support across all of Big Ass Fans' product lines. He holds a bachelor's degree in mechanical engineering from the University of Kentucky. David?
Thanks, Scott. Good morning, everyone. Always happy to be at AHR and help our friends AMCA put these sessions on. Thanks for coming to the first one. I know it's right as the show opens, so I do appreciate seeing all the attendance here this morning. Today, we're going to talk about heat stress, specifically mitigating heat stress with air movement in the workplace environment. We do have to do a bit of technical background to kind of level set, or at least that's what I'd like to do. Some of this is probably a bit redundant for a lot of you who think about heat transfer and things like that on a daily basis. But my goal is to kind of build a foundation to tell this story of thinking about our bodies and the physiological aspects of heat transfer and how that relates to things that we think more commonly of, whether it's coils or heat exchangers or things like that. I also want to provide a kind of a regulatory update of where and what the existing workplace heat stress standards are across the country. And then we'll talk a little bit about, depending on what problems you're trying to solve, what jurisdictions you're working in or are concerned about, what are some of the tools out there that can help you leverage some of the cooling effects you can get from air movement to get a better handle on not only the impacts and outcomes for your occupants in your spaces, but also how that ties back to these regulations that are becoming more and more common in several states. Lastly, we'll look at some air movement case studies, just some real brief examples, some of them more technical, some of them more subjective, that we've seen over the last few years doing this as part of our day jobs. So first, I have 4 quick slides here that are going to detail a couple of methods of heat transfer. Again, many of you probably know these way better than I do in designing coils and other HVAC equipment. But the first and probably most understood is conductive heat transfer. This is what happens when two objects of different energy levels, different temperatures come into contact. Energy, heat, temperature always flows from that higher energy object to the lower energy. And given enough time, those two things will exchange enough energy, enough heat to become the same temperature. We think of this as the sensation of walking barefooted or in socks across concrete, the hot handle of a cooking pan, or using an ice pack on your sore knee. Next, we have thermal radiation. This is the heat that we felt walking out here this morning. This is the sun coming in at that nice angle. It was a welcome reprieve for a lot of us who live north of here. But this is electromagnetic radiation. It's generated from generally higher temperature emittive sources that are absorbed by lower temperature, more absorptive sources. So whether it's a campfire on a cool fall night, heating lamps that we'll see down in the restaurants downstairs, or even, like I said, the sun this morning warming the earth, those are all great examples of thermal radiation heat transfer. My personal favorite, convective heat transfer. We have generally a solid object that is of differing temperature than a fluid, be it air or water moving around it. This is, to some extent, what makes our air conditioning feel good to us when it's coming out the vent on a car. But this is also the mechanism that we use to cool off our hot soup before we burn our tongue with it. And then we have evaporative heat transfer. I put this one right after convective because we can influence the rate of evaporative heat transfer with convective flows. So evaporative heat transfer is the heat that's associated with the state change of a fluid. Generally, we talk about it with water, but we could do it with other things, refrigerants, etc. This is the means that cools us when we sweat, that we use for direct evaporative or misting applications. And then, in condensers and things like that, we also apply the same concept in our larger scale HVAC equipment. Importantly, we can increase the rate of evaporative heat transfer depending on the conditions that we put the condensing medium into. So whether we increase airspeed or decrease vapor pressure to the outside, those are things that can increase that rate of evaporation and increase the rate of heat transfer away from that hotter, wetter object. So all four of these things combined, we can start talking about some more realistic systems, because rarely do you only have one means of heat transfer in real life. This could be as simple as cooking with a pan over a fire. A little bit more complex would be how we think about load calculations and heat gain and heat loss from our buildings that we design. And then probably even more complex than that is the human body. So that's the transition. I want us to think about the human body as a heat system that we can use all these different means to transfer heat to and from. Everything we do from a comfort standpoint or from a heat loss and heat gain is designed, our bodies are designed to maintain as consistent of heat load profile as we can. So on the heat gain perspective, we're still looking at those same four means, but it's conduction on a hot object, a piece of machinery. It's hot air blowing across as convection. It's the sun or these lights adding radiative heat load. And it's condensation from high humidity environments that limit our evaporative heat transfer. We also use these same things to provide heat loss. So conduction to a cool floor or a cold seat or something like this. Convection, a cold wind on a winter day. Radiation, you have a very old house. I know the corner of my couch, I could not be touching those walls, but I can still feel them sucking heat away from my skin temperature. And then probably most importantly, evaporation. So this is why we sweat. This is how our body rejects a large portion of the heat that we're going for. And whether you sweat more or your body changes skin temperature or things like that, all of this is done to try to make your heat loss equal your heat generation. And you can see there on the right, we have lots of things that influence both our generation and our loss. So everything from our activity, of course, to our basal metabolism, our posture. And on the heat loss side, these are all levers that are constantly moving up and down to try and meet that heat generation demand. So everything from respiration to evaporative sweat loss, and even changes to our skin temperature in forms of radiative heat loss. More generally, we tend to think a lot of this as thermal comfort. Obviously, we will talk about kind of the extremes of the thermal comfort world when we talk about heat stress, but thermal comfort is influenced by both personal factors, so what you're doing, what you're wearing, as well as environmental factors, which would describe the environment around you. ASHRAE has a thermal comfort standard 55. This does a really good job of setting forth how to evaluate thermal comfort and how to make sure you are designing spaces and controls to comply with the needs of your occupants regarding thermal comfort. Unfortunately, it's probably not used in the design phase as much as we on the committee would like, but it does serve as a really good basis for how to evaluate a lot of these different things. One thing that always gets pointed out with thermal comfort is that it is a subjective. It is this kind of balancing art and science to a degree. You can have statistically very advantageous thermal comfort conditions, and even then we know there's enough variance in the population that you will never get to 100% satisfaction for all your occupants in the room at all times. These 6 factors, obviously I think the personal ones are pretty self-explanatory. The more clothes you are, the more clothes you have, the more limited your heat loss potential is in a lot of ways. The higher your activity level, the higher your metabolic rate, the more heat you're generating. And so we think back to our balancing scale, we can see pretty quickly how these things can start to stack up if you're doing the wrong thing, or if you're working hard, wearing the wrong thing, and in a hot environment. On the environmental side, obviously air temperature plays a big perspective. This is like dry bulb air temperature. This is what we think of, of course, going over to the thermostat. That's the number we see there. Humidity not only has an impact on kind of the general acceptability of the environment, but also really can limit our evaporative heat loss potential. If the vapor pressure of the air surrounding us is so high that it's difficult to evaporate sweat, we lose a lot of potential there, and that scale starts to tip again. Radiant temperature, if you've ever worked in a restaurant or a bakery or something like that, you can attest to the importance of having those high heat sources nearby and how that can affect your thermal comfort. And then lastly, airspeed. There's lots of leverage you can have of airspeed, both from convective and evaporative means. And it's actually one of the kind of lower lower intensity things you can do in terms of energy profile to change the dynamic conditions of a space is to provide airflow to your occupants. So here we see kind of a general flow pattern from an HVOS overhead fan. We can generate a lot of coverage area from that fan as we deliver a column of air downward. It turns on the floor and develops what we call floor jets. So we don't really need direct exposure to a fan like this to deliver elevated airspeed to a large swath of our occupants in an open environment. The table on the right shows cooling effect on the y-axis and average airspeed for our occupants on the x-axis. And the different lines represent the different air dry bulb temperatures that these cooling effects can be leveraged at. So I like to show this because there's a lot of maybe confusion or misinformation that if your air isn't 72 degrees, that it can add heat to your occupants or not cool your occupants effectively. If we look at where we generally play a lot in commercial or industrial spaces, we're generally going to be in that like 200 to 300 feet per minute from like a HVOS fan or from a directional fan. Even between 77 degrees and 100 degrees, we're only looking at about 1 degree difference in the total cooling effect to that occupant. And we'll talk about at the further extremes of those conditions, just how effective air movement can be, even into the 105, 106, 107 degree Fahrenheit conditions that we see. I mentioned standard 55. The standard itself is, as someone on the committee, is admittedly a little confusing. My favorite thing that we've done in recent years, though, is fully integrate the CB Thermal Comfort tool. This is a great tool that's free on the internet. You can simply Google Center for Built Environment Thermal Comfort Tool, and you get this nice interactive thing where you can adjust those 6 factors that we talked about earlier. This allows you to do really easy thermal comfort analyses for your occupants. So the example we have on screen shows 85 degrees, no airspeed versus 85 degrees with 150 feet per minute of cooling. And we get all these metrics that really start to inform and characterize what exactly our occupants are experiencing. Perhaps most important of these is something called PMV. This is predicted mean vote. This is a scale of centered around 0 being perfectly neutral, perfectly comfortable. Negative numbers represent a sensation for your occupants that are cool, cold, and then positive numbers represent warm or hot experiences. There's been a lot of research done around PMV and taking the PMV theory and applying it to other applications. So one of these is this idea of, or not idea, it's this theory of that uncomfortable occupants are relatively less productive. And so what you see on the right is a graph from a study of construction workers plotting their relative productivity versus their PMV. So at neutral PMV at 0 on our axis there, they're right about statistically about 100% relatively productive. As we go to what we'd call warm, so a PMV of 2, they're still maintaining most of that productivity. But as we start venturing to 2.5, 3, 3.5, you start to see the steep diminishing returns of productivity relative to their thermal comfort. And I would say we start tiptoeing into heat stress, probably for most people about 3 on the PMV scale. And so if your workers are experiencing heat stress, not only are there the physiological aspects, which are very important, but there are also economic and commercial impacts to whatever the operation is at the time. If we think about the average worker, 4,000 hours a year, we know what their output is on an hourly basis. If we suddenly take 10 to 20% of that relative productivity away, that's a large chunk of money that our businesses are losing out on simply due to the environments that they're asking their workers to produce in. So back to our scale. We've talked about comfort, we talked about productivity, kind of talked about how to analyze it a little bit, but when do we start getting into this heat stress environment? This is when we've added all of our heat transfer modes and means up, and the sum of that gain is larger than the sum of our loss. And this can happen quite quickly if the magnitudes are quite different, but it can also happen over the course of hours or even days as we see successive higher temperature days in like a heat wave event. It's not uncommon for these effects and these syndromes to kind of accumulate on top of each other. Importantly, heat stress is a physiological condition. It's not I feel hot, it's not I am hot, it's that my body isn't working because it cannot shed the heat that it needs to. And it's not a mental capacity. It's not toughen up. It's none of that. It's a literal physiological limitation. So this is probably perhaps the most common metric associated with heat stress that many of you might be familiar with. This is the National Oceanic Atmospheric Administration's heat index calculator. So on our kind of y-axis, we have dry bulb temperature in Fahrenheit. Across our x-axis, we have relative humidity as a percentage basis. And we can see the combination of those conditions. Obviously, more temperature, more heat stress, more humidity, there's more heat stress. But the colors are important here because the green, there's really no risk for a healthy individual to develop heat stress. For the yellow, this is possible with prolonged activity. So this is perhaps like a high met rate environment or multiple days of exposure without any rest. But really, where we really start getting into trouble is this orange, red, and certainly never want to be in the purple zone. This is where heat exhaustion, heat illness is possible in the orange. And then we get to red, and it goes to heat stroke being possible to even likely. Heat exhaustion, everyone in the room here has probably had some form of heat exhaustion before. I hope no one here has ever had heat stroke because that's a very serious thing. So the difference, you might ask, heat exhaustion is a more acute condition. It's kind of the first signs that your body has a problem with the heat environment that it's in. So this often manifests itself as dizziness, excessive thirst, nausea, weakness. For those of us who are able and not obligated to keep working in an environment or something like this would be the first sign to maybe it's time to take a break. Maybe I'll take an early lunch. Maybe I'll go inside and work on something instead of continuing my work out here in the garden. And it's generally reversible in a fairly short amount of time. Fluids, cool the person down, etc. Heat stroke is again, very seriously, potentially fatal occurrence. We have all the symptoms of heat exhaustion, and you can get to heat stroke quite quickly from heat exhaustion. It doesn't take additional hours or additional days. Again, especially if the magnitude of our heat generation versus our heat loss is quite large. Heat stroke manifests originally as confusion or delirium even. So often people who are experiencing heat stroke, they do not have the neurological signals that their body is sending that there's actually a problem. So we knew it in the heat exhaustion state that probably time to take a rest. That's what kind of a sane person would do. But things can stack up so quickly that it tricks your body. You're not sweating anymore. You're not able to make logical decisions anymore. And it's just this really bad negative feedback loop that continues down a path until eventually you start having real physiological issues. So unconsciousness, vomiting, seizures, all of these are potential outcomes of a heat stroke environment. The best thing you can do in a heat stroke environment is obviously get the person to a cooler area, but call 911 emergency services right away. Because again, it is a very serious physiological condition. On the right, I thought this was an interesting graph. So what we have is obviously years on our x-axis, and then we have age-adjusted mortality rate per 100,000 person years. These are deaths that have been categorized as heat-driven or heat-related in the occupational sector. Obviously, we know there are a couple factors here. Our environment's getting warmer. That's kind of unquestioned at this point. But something is still happening. It's not getting warmer at a 3x rate, right? And so, to me, possible explanations here, we're doing better at realizing the risks of occupational heat stress and heat stroke. And so we're connecting events that might have been kind of discarded in the past and correctly categorizing them as heat events. But also we're starting to see these standards come in. And so the reporting requirements of the standards provide more states, more organizations tracking things like this really underscores, I think, especially as we talk about a warming environment and how to deliver safety and comfort sustainably in the future. This should be an alarm going off about what to do in those industrial and commercial settings. So what are some of these standards? So currently, the map on the left, the states in the blue, this shows where there are existing regulations connected to heat stress in the United States. So we have Washington, Oregon, California, Nevada, Colorado, Minnesota, and Maryland. Those are the 7 states of existing heat stress regulations. There are also 4 states with active legislation regarding heat stress standards: New York, New Jersey, Massachusetts, and Rhode Island. None of these standards are very much like the other, and we'll talk about the implications of that, particularly in kind of the new federal landscape here in a moment. But I wanted to highlight 5 of them. Given that we are at AHR, we're connected to ASHRAE, we're thinking about this indoor environment, built environment a lot. 5 of these standards are actually applicable to indoor workers: California, Oregon, Nevada, Minnesota, and Maryland. We have details in further slides, but to just show how different they can be, I have here the indoor conditions threshold. This is commonly a dry bulb temperature metric, except for one we'll talk about. And then, just like every other piece of legislation and regulations, there are all sorts of applicability exceptions in these. And so, for instance, Maryland, if your building has AC, kind of no matter how well the AC performs, your building is exempt from the heat stress regulations. In Nevada, if you're loading or unloading vehicles, that worker is exempt from heat stress regulations. So there's all these little carve-outs that make it really difficult to know exactly what applies to who. So next, we're just going to go kind of state by state. I've got 5 to 6 bullet points on each that I thought were key or relevant as I was reviewing all of these standards. Oregon, in the Oregon administrative section, you can see there. I'm not going to bore you by reading out those details. But this standard came into effect in June 2022. One thing to also keep an eye on here is how they define exposure, period. So in Oregon, exposure is defined as a 15-minute window in what they call a high heat environment per 60 minutes of work. They do exempt this high heat generation environment like bakeries or restaurants or foundries or things like that. Oregon standard does apply to buildings both with and without means for mechanical cooling. If your exposure exceeds a certain threshold in terms of dry bulb temperature, you do have to implement this work-rest schedule. So Oregon's first kind of block of that work-rest schedule is a 10-minute rest for every 120 minutes of work. If we think back to our kind of productivity thing, if we are in that environment, not only are we losing the productivity of when people are actually doing their activities, but now we have this 10-minute carve-out, about 8-9% of our allowable time per day that we also lose on our productivity basis. So these are things that businesses are thinking about of how they impact their manpower requirements, how they impact their facility requirements, and how they impact their forecasting on a production basis as well. One of the few commonalities between all these states' regulations is that pretty much all of them require very similar training and documentation processes. You'll see these referred to as HIPPs, or Heat Illness Prevention Plans. This is basically documentation that an employer or a building owner says, yes, we've thought about the high heat potential of this unconditioned space that falls under the umbrella of this standard, and here's what we're doing to train our employees about it. Here's what we're doing in terms of engineering controls when we do exceed. It's basically at its best, kind of a self-help guide of like, these are the things you should think about if you have heat stress in your space. Another commonality is that you'll see access to cool drinking water being an important point in a lot of these standards. A lot of these were probably brought over from the outdoor version of the standard, which generally existed before the indoor version of these standards in a lot of places. So we've all seen the orange igloo cooler on the side of the utility truck and things like that. That is there in a lot of times by state law. Oregon also says or lays out what some acceptable engineering controls are. So in the context of these regulations, engineering controls are, what do you do if you've done all the documentation, you've done all the training, and you're still in an environment where you cross this threshold into a high heat stress environment. So they provide that you can, of course, air condition your space, which can be practical for some places or very unpractical for others. You can provide heat shielding around some of your heat generating equipment. Maybe it's a ventilation hood right over your oven to get all that heat out of the building. You can add fans to provide cooling effect via an elevated airspeed. But a lot of times the exact engineering controls don't allow you to change the metric. So if you think about fans, for instance, fans don't change the dry bulb air temperature of our space. This doesn't change the humidity of the space. Oregon says it's an acceptable engineering control, but if it's 90 degrees and I'm providing cooling from my fans, I know I can get 5-6 degrees of Fahrenheit of cooling. I'm making strides to reducing heat stress, but the standard doesn't really provide me an exit ramp to claim success or to leverage that cooling effect into reduced break schedules or most importantly just like greater safety for my associates. Next, we have Maryland. This is one of the newer standards. This one came into effect September of 2024. Exposure here is defined as 15 minutes per 60 minutes of work. Notably, buildings with AC normally controlled at 80 degrees Fahrenheit or less are excluded. That is somewhat concerning language, I think, to me, because I think how you define normally there is important. Is normally a time average weighted thing of all 8,760 hours in a year, or is normally a design day? And what we see a lot is that even mechanically cooled facilities are acceptable for, let's call it, 3/4 of the year. But as summer production ramps up in a lot of our industries, we're running double shifts, we're making more parts in all these cooling categories. The weather outside is also hotter. And so even though our space is mechanically cooled, it might still be at 84, 85 degrees dry bulb in that space. And one of the problems I think with Maryland's legislation is that that building is then exempted from this heat stress regulation, even though there very well may be heat stress in that building. Again, you see the written heat-related illness prevention and management plan. This is the same thing: drinking water, rest areas, engineering controls, etc. Notably in Maryland, the work rest schedules are also above 90 degrees, beginning 10 minutes for every 120 minutes. And the standard talks about alternative cooling and control measures. It's not as detailed or as specific as Oregon or some of the other states, but notably, if an employer demonstrates effective heat illness control via a fan or via AC or evaporative cooling or whatever it is, the work rest schedules may not be required. Again, kind of nebulous language, but what I like about that, at least, is it does provide you an exit ramp to show success. You're investing in these cooling solutions. You've done your HIPP. At least there's a way to meet somewhere in the middle on it. Minnesota actually has some of the oldest heat stress related regulations in the U.S. They started mostly as outdoor related, but have been brought indoors in the last 10 years or so. One of the weird things, or one of the nice things about Minnesota, is that it uses wet bulb globe temp. So wet bulb globe temp basically takes into account all of the factors we've talked about in terms of heat transfer or thermal comfort, and you can show numerical quantitative improvements by reducing the radiant heat load or by increasing the airspeed in your space. It is probably the best way to measure heat stress, aside from actually measuring like core temperature, things like that. But one of the limitations of it is that how many of us have a wet bulb globe thermometer, period, much less a matrix of them that we can put in all of our 10 facilities across the U.S. that we own and operate. So there are barriers to thinking about wet bulb globe temperature this way. I think it's one of the key questions to figure out is what metric do we all want to agree on and push towards? Like, how do we do allowances for perhaps fans or allowances for evaporative cooling without having to go and outfit our commercial industrial building stock with millions of these wet bulb globe thermometers? Minnesota also has some different categories for depending on the MET rate that you're doing. So for their heavy work category, their wet bulb globe exposure limits are 77 degrees Fahrenheit versus their light work is 9 degrees Fahrenheit above that. Again, some commonalities. This heat stress and illness training is mandatory to be provided. They actually have a separate regulation that defines exactly what that is. This kind of 5205 also has a section specifically about ventilation and how to use ventilation to change the heat stress profile of a building, as well as how to limit cold exposure in environments like maybe truck loading and unloading in the winter in Minnesota. You kind of have the opposite problem of where you have this cold environment exposure that can be just as dangerous as the heat exposure. Nevada is the newest state to have a heat stress regulation. This one just became effective in November 2024 and became enforceable from the beginning of this month, February 2025. Again, we have this kind of requirement to establish a written safety program. Exposure here is different. So the past we looked at were 15 minutes in a 60-minute window. This one's 30 minutes in a 60-minute window. Employee training programs, all of this. Nevada is the one we pointed out earlier that has all the exceptions carved out for mechanically cooled spaces, regardless of kind of how effective those mechanical cooled systems are, as well as the loading and unloading of vehicles. I think that one's of particular importance. We see a lot for in the environments that the company I work for goes into. A lot of the conditions in the interior of the facility and even in the loading dock adjacent space is quite good. There are things you can do quite easily there, but it's really hard when you have this big metal box parked out in your warehouse yard for hours at a time, just getting blasted by the solar load and the environmental load, and you back that, big, it's got boxes and boxes and it's got a lot of thermal mass now. You back that up into your building and then you ask, two of your associates to go in and touch all that, to interact with it, to gain all the heat from that environment as they unload that truck. And so it's one of the more demanding and probably risky activities that can happen in the general warehousing and manufacturing environment. And I think it's one of the larger problems to solve in those environments as well, as how do we tackle that trailer cooling environmental control piece without just strapping on basically split units to every DOT trailer that's going down the road. California is probably the state regulation that has gotten the most traction in media and things like that. It came into effect in July of 2022. Again, we have this heat illness prevention plan. We have heat illness training. California is one of the only states that has a prescriptive heat acclimatization period, drinking water, rest breaks, and then the legal requirement to provide first aid. So this is a good piece of language, I think, that effectively there is someone designated in your heat illness prevention plan as the heat stress liaison, as it were, for your facility. And their core responsibility in that capacity is to monitor your employees for heat stress and heat illness. So to the effect that we see that they were to see heat exhaustion, to stop that before it turns into heat stroke and becomes a much more serious thing. California also has probably the best language as it relates to the requirement to measure conditions in pretty much every space where you have high heat potential work going on there. And it also requires you to maintain those records. So there's some accountability that you're actually monitoring and thinking about the conditions in the space for the entirety of the year, as opposed to just taking a couple measurements in the middle of April, in the middle of October, when conditions in your environment are generally more acceptable. California also does a good job of detailing what acceptable engineering controls might look like. So everything from evaporative coolers, ventilation, fans, heat shielding. These are all the same things that us in the room and these kind of EHS professionals who are writing this regulation agree that are good means of improving environments. But where California falls short, just like Oregon, is that they kind of don't define what success looks like. So if I improve the environment through reduced humidity or airspeed or radiant shielding, that's great, but none of it really affects that dry bulb temperature metric that all this is driven on. Lastly, we have federal standard. So in 2021, federal OSHA kicked off a docket titled Heat Injury and Illness Prevention in Outdoor and Indoor Work Settings. So this would have been the first federal heat stress regulation of its kind in the U.S. I admit there's been a lot of movement in this since I made the presentation. Since I made this, the kind of the most recent thing was in late August, there was a notice of proposed rulemaking document that was put on the federal OSHA website. That comment period closed in January, mid-January, with more than 27,000 public comments. We think about something like ASHRAE 90.1 as being kind of a contentious thing that people fight over, and they want to make sure that it's doing what it sets out to do, and there's vested interests from different parties and things like that. For an entire revision cycle of 90.1, there might be 200 comments, 200 public comments. For this regulation to get 27,000 public comments is unprecedented. There are wildly impactful things that have never gotten more than 100 public comments on these governmental websites. The comments, when you dove into them, were actually really interesting. Usually you see just general lobbyists or commercial stakeholders or things like that, but through whatever means, you actually had real frontline associates going in and telling their story of an environment they worked in where they, are now disabled, or they've never felt the same after working in these environments, or whatever their personal story is. And there were thousands of these comments and stories just like that. And so it was really, encouraging, engaging for I'm sure the people that were developing this standard to be like, wow, like look at all of this, coming out of the woodwork, that all the problems that we're solving. I think that speaks also to the mortality graph that we saw too, of like this might actually be an increasing frequency problem, whether it's climate driven, just labor standard driven, or whatever the case is. Seeing all 27,000 of those public comments was interesting for this. However, with the change in administration, it's now, I'm not sure if it's been officially withdrawn yet, but this is probably never going to see the light of day. The risk of that, from my perspective, the biggest risk, just like with many other regulatory things that we as an industry talk about, is that, okay, with no kind of federal overriding standard or no federal guidance from states of how to pull language or to make sure that the regulations we're making actually do what we want them to do, the risk now is that all 50 states have their own heat stress regulation. And for companies that have buildings or work sites or whatever across the country, keeping on top of those and being compliant to all of them at the same time is going to be quite the task. Additionally, there's a bit of a philosophical question of, should a worker that's maybe 5 miles from another worker be protected to a less effect if someone is in Utah where there's no heat stress regulation, but just across the street in Nevada where there is heat stress regulation, like the climate isn't any different, the work isn't any different. One truck goes from both across the state border every day. It's becomes a mess, for lack of a better explanation. So I think the title of my presentation was Using Air Movement. We've talked about how air movement plays into the standards a lot, and how it can impact how our body systems gain or reject heat. But taking that into actual application of fans and air movement into these spaces that are at risk of heat stress, the workers are. One thing I always like to level set as an applications engineer is that there's no turnkey silver bullet solution. We're looking at 3 different areas from the same facility, and it would use 3 different types of fans. And some are more suited to evaporative fans other than overhead fans or directional fans. Even different, facility types for the same company might require a different optimal solution. And so I'm really using this to advocate to working with, the manufacturers of all of these kind of engineering controlled products directly to, let them into what your processes are in your facility so they can develop the best processes and the best tools to help you meet your heat stress goals. A lot of these tools are freely available. So I'm a big friend of the Center of the Built Environment at UC Berkeley. I think they do great work. They have a free fan design guide tool on their website. You can see it there, or again, Google the fan design guide, Center for the Built Environment on the internet, and it'll take you right there. It is effectively a textbook of what and how and why to use air movement in both conditioned and unconditioned spaces. It's a great resource for those of you who are practitioners, designers. It'll even show you how to integrate with mechanical systems, sequence of operations. Practically everything you want to know specifically about circulating fans and ceiling fans can be found here in this document. The design tool actually uses a lot of the information and guidance in that document to parameterize fan design for a space. So you can tell it kind of the area of concern you're looking at, what the dimensions are of that space, if you have a target airspeed that you found using the CBE thermal comfort tool to meet a certain set of conditions. You can use tools like this to optimize that design with real fan performance data. We briefly mentioned earlier the kind of limits of cooling for fans in high temperature or high humidity environments. If that is a question in designs, the Center for the Built Environment also has this fans and heat tool. So you basically build an occupant profile, what they're wearing, what they're doing, as well as what airspeed you're generating across their occupied space. And you get this nice graph that you see on the left side. So you see the 3 different colors there. There's a large swath of that graph for our, we have temperature on the operative temperature on the y-axis, relative humidity on the x-axis. A lot of our conditions, there's no heat strain. That's that kind of light green color. Even in high temperature or relatively high relative humidity situations, fans are still beneficial of tipping that scale in the other direction. There was, I think, both NIOSH and Cal OSHA at one point had guidance that for air temperatures greater than 97 degrees, which is assumed to be basically your skin temperature with a base metabolic rate, that fans were not acceptable for reducing heat strain on the body. It was a flawed metric that really didn't come from anything other than what we know the skin temperature is. There have been some recent work from universities that have shown basically this exactly, which is that even up to 104, 105 degrees Fahrenheit at 50% RH, you still have enough evaporative potential by using increased airspeed across a wetted skin to actually pull heat off of that environment or off of that system. Even though convectively, theoretically, you might be adding heat, the evaporative losses outgain your convective gains. That's probably one of the larger mistakes or misconceptions that I see in practice, is that the idea that there are certain temperatures commonly that fans are not applicable in, or that we should turn our fans off above 90 degrees Fahrenheit or things like that. I'm thrilled with this tool. I use it more than I should have to explain this to customers or whoever I'm talking to, but it is good. And I think it really speaks to, again, this idea of the human body as a system. It's not simply just hot air blowing across you. There are other methods of heat loss going on as well. One of the questions that always comes up in 55 from practitioners is, well, how do I determine what airspeed I'm going to achieve from this fan design layout? We showed the CB Thermal Comfort tool, but it's kind of a open box. It's kind of an optimized thing. There are manufacturers out there of air circulating and ceiling fans that now have specific CFD tools to take architectural layout of the space you're working in, or even if it's an existing space, basically turning pictures and site visit information into a real parametric model that then CFD analysis can be done on. And we can use those CFD results to start to generate some of the thermal comfort calculations and some of the heat stress calculations that are common in standard 55 to get to at least a range of discrete answers to answer what like airspeed or temperature profiles or things like that might be in spaces. So these are really helpful to explore a wider range of conditions than you might be able to observe on a short design window or a short time frame project basis. So a couple of these examples here, we're back in a kind of fulfillment center environment. These are workstations that are kind of hard to get to. They're narrow walkways and they're generally surrounded on 3 sides by processing equipment. But we did some surveying and some questions of the actual associates in that space. The first of which was, what makes your work area uncomfortable? The most prominent answer there was no airflow. So that's great. It shows that associates know that airflow is a means to control their comfort, or at least one that they're used to having. We asked when their work area was uncomfortable. Unsurprisingly, this is in the afternoon. So if we think about heated and ventilated only spaces, generally they're pretty good if they're controlled correctly of shedding their load overnight when they're unoccupied. But as more work is done throughout the day, and as the sun starts adding solar load and we have our temperature load as well, conditions become basically uncomfortable the longer that building is operating and at peak. So we installed the fans, got about a 8-degree effective temperature difference. You can see the predicted mean vote shifted from 0.5 to negative 0.5, and overwhelmingly positive response to the fans, at least in terms of noticing them. When we originally presented this data, the customer was kind of alarmed by the fact that a large percentage of the associates did not notice the new fans. To me, that was like really good because like we put them there, they're up out of the way, they're not causing disruptive airflows, we're not blowing papers around, things like that, because we still ask these same associates about their comfort. So whether they did or didn't notice the fans is kind of fine by me, as long as they're actively or even passively aware that their conditions are better. It was kind of mission accomplished as far as I'm concerned. This is some work we've actually shared as part of these AMCA education sessions before. This is a collection of building energy models that were simulated as heated and ventilated only warehouses in each of these climate zones and locations that you see. So without any means of engineering controls, you're able to basically calculate the heat index for every hour of the year inside of this facility. So the furthest left table, there are 3 tables here. The furthest left table shows the heat stress, heat index profile for a building, all 8,760 hours of it in each of those locations. One of the problems we talked about is potentially this shift in climate that is driving a lot of these heat illness issues in climates and in buildings that have historically performed fairly well. So what we did is we took the future weather profile of the cities on the left, matched it to what the future weather would be like based off of a Zurich ETH study, and compared how that heat stress risk profile compared. So what we mostly see here, to contextualize, is a lot of hours moving out of our green, like no risk zone, into the yellow and red and orange risk zone for either heat exhaustion or, unfortunately, heat stroke. The question was then asked, okay, we know what our future profile looks like for these buildings that are going to be in service for another 30 years. What if we add fans to that environment? Same dry bulb temperature, same relative humidity, but we know we're still able to remove heat from the occupants. That, on the right side, is the resulting heat index profile. Heat stress, heat index risk profile. And you can see that even in the hottest environments, the Miami, Houston, Phoenix, we're able to reduce the highest risk, the very hot category, significantly, going from 1,000 hours a year to under 100 hours a year where that high risk situation occurs. For operations of a facility or just risk mitigation for a business, like that's a huge improvement. Productivity aside, if you could tell an EHS person that you are now 10% less likely to have any sort of incident, much less something as serious as heat stroke, most of them would make that change or make that process change, that purchase as soon as they could. I mentioned trailer environments. This one is still generally, I would say, a tougher nut to crack. One of the things that has been tested recently is something that actually atomizes water to take advantage of that state change, kind of leverage some of that energy that's built up in that liquid water and see if we can drop the dry bulb temperature of the air inside that trailer. Might be hard to see depending on the resolution of the screen, but there are 2 colors of lines here. There's a blue line and there's a black line. The black line is effectively the control. So there's no fan device, no atomizing device in that trailer. And then the blue lines represent the trailer with the atomizing device in it, measured both kind of front of the trailer, back of the trailer, middle of the trailer. What we saw is large dry bulb temperature depression in the space without large increases in the relative humidity of the trailer air. And as we talk about kind of go back to our limitations of what fans can and can't do in terms of heat strain reduction, yes, it might only be 5 degrees of cooling, but if we're taking it from 110 in the trailer to 105, where then we also start to get the cooling effect of the airspeed and the evaporative and everything else, we've turned it from an environment where we don't have a solution to actually drive occupant cooling and heat stress reduction in that space, to one where even a simple airflow from the fan can make a large improvement. So a couple of more subjective ones. This is from a manufacturing environment that was actually mechanically cooled. Before the fans, heat complaints were a daily event. As a matter of fact, I didn't hear any complaints from employees this summer. This is the first year I can say that. This is from another manufacturing environment, talking to the production capability aspect. Our guys increased production from 10 units to 16 units per week, a 60% increase. It's unbelievable. So that's probably above and beyond what we would expect from just the PMV shift of comfort. It's not the same with Jackson you're thinking of, I don't think, at least. But it still speaks to, again, this kind of, a lot of times there are subjective things that go into thermal comfort and to thermal sensation and things like that, where actual applications can outperform what the models would say is possible. My last one is a warehouse that shifted from lots of forklift traffic. So forklift traffic is actually really good for if you're on the forklift for heat stress, because you're moving through the air without having too high of a metabolic rate. You're kind of taking your own personal air movement device with you as just you travel through the space. But this company transitioned from an environment like that to more of an automated material handling standpoint, where now you had operators in place for long periods of time, not moving. And so they started having heat stress issues and worked to solve them by adding an airflow to basically replicate what the previous associates were feeling on that moving fork truck to operators who were there for longer periods of time. That's all I have. I think we have a little bit of time for Q&A. Scott would like me to probably say that to actually receive your PDH here, you do have to do the post-course evaluation. But yeah, I'm happy to take any questions here that we have time for, or I'll stick around for a few minutes after the session here too to be happy to talk. Great. Thanks.